this video, we're going to be talking about probability assignments. So it's important to know what probability is talking about. The probability of an event occurring is between 0% and 100%, or between 0 and 1. If the probability is 0, that means the event is certain to not happen. And if the probability is 1, that means the event is certain to happen. And it can take any value in between 0 and 1. And we usually express probability as a fraction or a decimal, though percents are also acceptable. This is the formula for probability, which you will almost never use because it's sort of common sense. But it basically says the probability of a set A, or of obtaining something in set A or event A, is the number of elements in A, that's what the N stands for, number of elements in A, divided by or set up as a fraction over the number of elements in S, where S is the sample space. So, for example, calculating simple probabilities, let's find the probability that each of these following events will occur. That's like event A. For the random experiment, rolling a fair dice. So we're talking about the numbers 1 through 6 as the sample space. So the sample space for this is 1, 2, 3, 4, 5, 6. And then we have to think about each event. So for part A here, it says rolling an odd number. So I will not make you show all of this work, but we could imagine that this is the event A. The odd numbers are 1, 3, and 5. That's the sort of the subset of S that includes the odd numbers. And so the probability of getting something in that is the number of elements in A, which is 1, 2, 3 things, divided by the number of elements in S, which is, as you know, 6 things. And so the probability of getting something in what we've called event A is 3 out of 6, which reduces to 1/2. So do you need to do all of that work? Probably not for something as simple as this, but I did want to show you how that formula could be applied. Probability of rolling an even prime number, there's only one of those, that's the number 2. So 1 out of 6 possibilities will be an even prime number. The probability of rolling an odd prime number, the odd prime numbers in 1 through 6, if we go through the list, are 3 and 5, so 1 is not a prime number. So there are 2 odd primes out of 6, which reduces to a probability of 1/3 that the number you roll will be an odd prime. And the final one, rolling a number that is either prime or even. So here I'm going to list out that set. So what's included in the set? Either prime or even. So 1 is not included. 2 is included because it's even. 3 because it's prime. 4 because it's even. 5 because it's prime, 6 because it's even. And so there is a 5 out of 6 possibility that you'll roll a number that is either prime or even. Okay. So a dice does not need to be 6-sided. Here's an example of a 20-sided dice. Faces are numbered 1 through 20. The event A is defined as the number obtained is a multiple of 4. So we want to think about, out of the numbers 1 through 20, the multiples of 4 include 4, 8, 12. This is what multiples are, right? 16 and 20. So to determine the probability of A, we're counting the number of elements in set A, which we just listed out. That's 5 elements. We're thinking that on the list of numbers 1 through 20, there are 20 elements. So the probability of something in event A happening is 5 out of 20, which reduces to a 1/4 probability. And then it says the dice is rolled 100 times. How many times would you expect to get a multiple of 4? So this is thinking about probability as a long-term trend. So if I was to roll the dice 100 times, about 1/4 of the time I'm going to get something in event A, and 1/4 of 100 is 25 times. You could just do 1/4 times 100 to get that. So some probability rules that we'll be going through starts with this, which is the concept I mentioned on the first slide. Rule 1, the probability of any event takes a value from 0 to 1. Written symbolically, that looks like this. That probability of A, whatever event A is always going to be greater than or equal to 0 and less than or equal to 1. So something between 0 and 1. Rule 2 is that all possible outcomes together have a probability of 1. So this is like the probability of getting an odd or an even number, right, is going to equal 1. So all possible outcomes together have a probability of 1. Or you could think about it as way this formula is written, the probability of getting something in the sample space is 1, because it is certain that if you roll a dice, you're going to get something in the 1 through 6 sample space, right? So probability is certain if you're doing the probability of the overall sample space. Rule 3 has some new vocabulary words on it. So for disjoint or mutually exclusive events, that's this 2 different words that mean the same thing. That's not 2 different things. So disjoint is another word for mutually exclusive events. And if you think about, before I even read the rest of this slide, mutually exclusive events are just either one happens or the other, but both cannot. So odd and even is a good example. On a Venn diagram, that would be like 2 circles that do not overlap, because if I was rolling a dice, I would have the even numbers in one circle and the odd numbers in another, and there's no way that I could roll a single number that would be both odd and even at the same time. So for mutually exclusive events, the probability of one or the other happening is simply the sum of their separate probabilities. This is called the addition rule for mutually exclusive events. It is in our formula booklet, and it only applies for events that do not overlap. So if we wanted to do, I think we probably have an example of this on another slide, so let's keep plugging along here. Here we have the probability of an event not happening is equal to 1 minus the probability of the event happening. These would be called complementary events, so another vocabulary word. It makes it look super confusing in this sort of strange version of a Venn diagram. I prefer to think about this as, here's circle A, and if something in A doesn't happen, then something in A prime does happen. So you've basically got the complement, meaning everything outside of A, also known as not A. So you can think about this as the probability of not A happening is going to be equal to 1, which is the overall set, minus the probability of A happening. And the same thing works vice versa. This is sort of common sense. Here it's just the notion of the vocab word complementary that you need to have down, and you need to understand that notation with the little apostrophe, which I might read as A prime or not A. So here's some examples of applying these rules. So here's some data. So we're going to do some probability with data, which is interesting. Data collected for traffic violations was collected in a certain country, and the summary is given below. And we're asked to calculate some probabilities. What is the probability that a randomly selected offender here is A, in the youngest age group? So the probability of being in the youngest age group here, the probabilities are right there on the table. So we don't have to think too hard. We just have to figure out which ones we're adding together. In probability of the youngest age group is right on the table. It's the 0.06 probability. So here's an example of probability being given as decimals rather than fractions. B says the probability that the offender is between 21 and 40. And so for between 21 and 40, we're talking about adding these numbers together. So 0.47 plus 0.29 will be 0.76. And probability for part C here, that the offender is younger than 40. So younger than 40 is going to include all of these folks. So basically just add 0.6 or 0.06 to the total from part B, and we will get 0.82. So pretty simple, adding separate probabilities together, which you can do for mutually exclusive events. So that rule, though it seemed probably a little confusing, in application is really very simple. Are these age groups mutually exclusive? Yes, because a single offender can't possibly fall into more than one of these groups, right? These would be 4 separate circles if we were doing a Venn diagram of the young folks, then the 21 to 29, then the 30 to 39, that would be a whole separate circle, and over 40 would be a whole separate circle. So when you have separate circles or mutually exclusive events, you can add their separate probabilities together to get the probability that one or the other is going to happen. That's the addition rule for mutually exclusive events in action. Here's another example that we can use applying our rules. So we've got when people create codes for their cell phones, like a login number, the first digits tend to follow this distribution. So a lot of people choose 1, 2, and 3 as their first digits. As you can see, those probabilities are significantly higher. Almost nobody chooses 0 as their first digit. And then also descending as you get up towards 9, fewer and fewer people choose those for the first digit of their cell phone login. And so here we are asked to, again, calculate some probabilities from the table. Again, these are mutually exclusive events because there's no way the first digit of your code could be a 2 and a 9 at the same time, for example. So here, part A, find the probabilities of the following three events. A, that the first digit is 1. So the probability that the first digit is 1, we're just reading it from the table. B, the first digit is more than 5. So for more than 5, we're going to have to add together these four probabilities. You should have had a calculator handy for this. Let's see what that comes out to. So I'm just taking out a calculator to add together those four decimal probabilities. So this would be on a calculator portion of a test. They tend to put decimal questions always on calculator portions of the test. So that comes out to 0.221 if I'm doing three significant figures. And then C, the first digit is an odd number. Okay, so for the first digit being an odd number, we can add together the separate probabilities of 1, 3, 5, 7, and 9. So again, just applying the fact that because these are mutually exclusive events, we can add their probabilities together to get the probability that something will be either 1 or 3 or 5 or 7 or 9, and it comes out to 0.603. You could check me on that addition, but even if I'm wrong, you get the idea that we're adding together the 1, 3, 5, 7, and 9 probabilities, which we can do because these are mutually exclusive events. And then down at the bottom of the slide here, it says, find the probability that the first digit is 1 or greater than 5. So let's change colors so you can see where I'm working. 1 or greater than 5 means to add together the 1 or greater than 5 probabilities. In the interest of time, I'm not going to perform that addition, but you understand the idea that, again, we're just applying the fact that we can add these together. Let's see, we've got the probability of being not 1. That's an interesting one because there's a faster way. The probability of being not 1, I could add together the 0, 2, 3, 4, 5, 6, 7, 8, 9, or I can apply the whole notion of the complement. So for here we have not being 1. You could think about this as 1 minus the probability of actually obtaining a 1, right? So this is sort of the probability of the complement will be equal to 1 minus the probability of A. So if we define A to be 1, then 1 minus that probability will get us basically all the other probabilities added together. So it's the complementary rule in action, but it's so common sense you almost wouldn't need to use the rule in order to get it. You just need to think about, well, the fastest way to add together all the other probabilities is probably to take 1, which I know is the total, and just subtract the 0.3. So the probability that it's not 1 is going to be 0.7. Put a couple of extra zeros on there for 3 sig figs. And then the last question here, an odd number or a number larger than 5. So for that, we're adding together the odd numbers or a number larger than 5. So we're going to additionally put the 6 and the 8 on there. We've already included the 7 and the 9, so we do not need to add them again. And I would just take all of the red circled numbers and add those together in order to answer the last question here. And then just an introduction to a tree diagram. We'll do these much more throughout the rest of the chapter. But a tree diagram is not like a Venn diagram. It's a different way of representing simple events. That's a nice visual. You only want to use these if there aren't many outcomes and if one event follows another. And you could almost think about this chronologically, almost like following another one as in coming after it. So this might be like you reach into a bag to pull out a marble, then you reach into the bag to pull out a second marble. So that would be one event following another event when you're then going to be asked about probabilities, for example, of like obtaining 2 red marbles. Or you could think about it as you're randomly selecting 3 juniors from the junior class. So you'd select one, then you'd go back to the list and you'd select another, then you'd go back to the list and you'd select another. So that's going to be like a tree diagram situation because it's one event followed by another event followed by another event. The tree is that if you have, let's say, red and white marbles in a bag, right, there aren't many possible outcomes. If you reach in and grab a marble, you're either getting a red marble or a white marble. And then if I was to reach back in to get a second one, so this is the event following another event, then off of the red branch, let's say you obtained red as your first result, well, your next result could still be either red or white, assuming there are still some red and white marbles left in the bag. Or if you obtained white on your first grab, This second grab could again be red or white. And so we've branched off into all of these possible pathways because it's an event happening after another event. So we've basically got a branch for each event here, a branching, I should say. Like this is one branching, and this is the second branching. Let's see if we have some examples to practice tree diagrams. This is a good one. So here we've got two fair dice that are rolled. One is red and one is blue. That's the two events here. So first we're rolling the red dice, then we're rolling the blue dice. So branching 1 is for the red and branching 2 is for the blue. It might seem like there are too many possible outcomes when you roll a dice, and indeed I wouldn't want to do a tree diagram that had 1, 2, 3, 4, 5, and 6 at the end of all these different branches, because at the end of that I would then have to do another branch of 1, 2, 3, 4, 5, and 6 for each of those. So that would be a really painful tree diagram to draw. But if I look at all of the questions here, they're all about either rolling a 6 or not rolling a 6. And so there actually aren't many outcomes that we really need to consider here, just because of the wording of this question. So let's say I roll the red dice first, and either I'm going to get a 6 or I am not going to get a 6. Those are mutually exclusive outcomes, right? I'm either going to get a 6 or not get a 6. So tree diagrams only work for mutually exclusive events where there aren't that many outcomes because we just don't want to make a tree. If there are like 6 different colors in the bag of marbles, I wouldn't want to make a tree. It's just going to be, there's got to be a faster way to get there. But here we can do 6 or not a 6. And the probability of obtaining, let's say, the probability of obtaining a 6, actually, let me do the next branching first. So I should say after we pull out the red, we're going to go back and roll, or after we roll the red dice, we're going to roll the blue dice. And again, we could obtain a 6 or not a 6. And if we didn't get a 6 and we rolled the blue dice, well, again, we could obtain a 6 or not a 6. So that's the tree diagram of the rolling of one dice followed by the rolling of another. But along here, along each of these branches, we need to put the probability so we can actually use this tree to help us calculate some probabilities. So when I roll just the red dice, okay, so I'm just looking at this red dice over here. What is the probability that I'll roll a 6? Well, there are 6 possible options, and only one of them is a 6, so 1/6 chance. Notice I label it right along the arrow. So I have a 1/6 chance of heading down this arrow. I have a 5/6 chance of heading down this arrow. The probabilities for on the blue dice over here, so now we're on the second branching, are going to be the same. I still have a 1/6 chance of rolling a 6 and a 5/6 chance of not on my second roll. And so now I have all the 4 possible options. I either roll a 6 followed by another 6, a 6 followed by not a 6, a not 6 followed by a 6, or a not 6 followed by another not 6. And now I can answer all the probability questions you could possibly be asked using our tree diagram. So, probability that a double 6 is rolled. Well, we've got 1/6 a chance of getting the first 6 and a 1/6 chance of getting the next 6. This is getting into a little bit of a rule we haven't covered yet, but in order to get to the end of this branch, I can multiply 1/6 times 1/6. So each of the branches I multiply along to get to the end of the pathway. And there is a 1 in 36 chance, this is for part A, that I roll a 6 followed by another 6. For part B, no 6s are rolled. So this is not a 6 followed by another not a 6. So 5/6 times 5/6. We always multiply to get to the end of a branch. So 25 over 36. C, exactly 1/6 is rolled. Here we've got 2 pathways to consider. So exactly 1/6 being rolled, green now, is 6 followed by not a 6 or not 6 followed by 6. So I actually have both green pathways meet the conditions here of part C. So I'm going to multiply each one. So 1/6 times 5/6 for the first option. Or, and I can add this because it's totally mutually exclusive, 5/6 times 1/6. So I'm going to calculate each pathway, then add the 2 pathways together that apply for part C. So each one of them ends up being 5/36. So 10/36 overall. So multiply to get to the end of the branch, and then add different branches together if you need to. And then the probability for D here, that at least 1/6 is rolled. So at least 1/6, see if I can change to yet another color. At least 1/6. Well, This is at least 1/6 because it's 2 6s. This is at least 1/6, and this is at least 1/6. Well, I don't want to do all those 3 pathways added together because I could instead just do 1 minus the pathway that doesn't meet the condition. So that's from the complementary events that we talked about earlier. So 1 minus the probability of the non-included branch here, the not 6, not 6. I already calculated that that is 25 over 36. So I'm just going to do 1 minus 25 over 36 to figure out that the probability of getting, oh no, that's not right. The probability of getting at least 1/6, oh yeah, that is right. So the probability of getting at least 1/6 is going to be, let's see if I can do that subtraction, 11 over 36. Okay, and that is all.